Hello, everyone. Welcome to pre-lecture 12. Today we're going to be talking about Le Chatelier's principle, which is something that deals with shifts in our equilibrium values. And so to just kind of start out with defining Le Chatelier's principle here and review what we've already talked about, we know that when a system is at equilibrium, we have this dynamic balance where our forward and reverse reactions are going to be going at equal rates. And so, of course, sometimes things change in our reaction conditions. We can have something called a stress that could be perhaps a change in concentration or temperature and pressure that make the rates of our forward and reverse reactions no longer equal. And that would mean, of course, that our system is no longer at equilibrium. And so this phenomenon is summarized by Le Chatelier's principle that states that if an equilibrium system is stressed, then the system will experience a shift in response to the stress that will move it back to equilibrium conditions. Okay? And so if we think back to properties that will affect the rate of our reaction for kinetics, two of the main stresses are changes in concentration or changes in temperature. We're also going to mention pressure today as well. Okay? So let's start with changes in concentration. And let's use this reaction shown here as our model reaction where we have H2 gas plus I2 gas yielding 2 moles of HI, which is also a gas. Okay. And so one way that we could think about Le Chatelier's principle is through a kinetic interpretation. We know from everything we've covered in chapter 12 that if we were to write a forward reaction for this reaction shown here, we have H2 plus I2 yields 2HI, and we could write that rate is equal to some rate constant times H2 to some power times I2 to some other power, right? We could also write a reverse reaction for our products going back to our reactants, and that rate would have a different rate constant, a rate for the reverse reaction, and it would be multiplied by the concentration of HI to some power as well. Okay? And so we know that at equilibrium, our rate of our forward and reverse reaction will be will be equal. However, if we add more reactant, then the rate of our forward reaction would increase. We know this because the rate of this reaction is dependent on our concentration of our reactants, right? And so as the rate of this reaction increases, that will reestablish the equilibrium. It will also decrease the rate of the reverse reaction. And so this will ultimately decrease ultimately decrease our product HI, the reverse reaction there. And so the same would be true if our product were removed from the system. So adding reactant or removing product would cause the same effect. Okay, and of course the reverse would also be true, that if we added more of our product, the rate of our reverse reaction would increase, leading to a shift in the equilibrium. And that says right, but I'm realizing now it should say left. So if we add more product, the rate of our reaction should shift ultimately towards our reactants. Okay. So the other way you could think about this is the way I would recommend thinking about it. Has to do with thinking about things in terms of our reaction quotient, Q. Okay. And so one of the ways we can think about Le Chatelier's principle here is through our reaction quotient. And so if we were to write out our products over our reactants raised to their stoichiometric coefficients for the same reaction, this is what it would look like. And of course, Q is equal to K when things are at equilibrium. So if a reactant were added to the system, either H2 or I2, then our denominator would grow larger, which would mean that we would have to produce more product in order to reestablish our equilibrium value of K, right? If our denominator grows larger by adding things in, we need to create more product by shifting our reaction to the right in order to get Q back to equaling K. So for example, if more H2 was added, then our reaction would shift towards the products and equilibrium would be reestablished with more H2 and more HI being present. However, we would have less I2. And so this can be actually a very useful strategy for getting our reaction to go to completion. So if we don't care if we add excess H2, we could basically get rid of all of our I2. If we just keep adding H2, we would keep forming HI until eventually we have no I2 left. We just have H2 and HI present. Okay, so that's something to consider. Of course, when we're considering our reaction quotient, we always want to compare it to K. And so if Q is greater than K, then the reaction would shift towards the left. And if Q is less than K, then the reaction would shift right. And that is something that should be something that we review, that is a review from our last class. Okay. All right, so that was concentration. We can also think about a stress on an equilibrium system being due to changes in pressure, because concentration and pressure are related through our ideal gas law. Any change in pressure can also result in changes in Q. Okay, and so if you consider this reaction here, where we have 2NO2 on our reactant side, and then we have 2NO and O2 forming on our reactant side, we could express our equilibrium expression in terms of the partial pressures for all of these chemicals using this expression here. Okay. And so say, for example, our container were to be compressed to become 3 times smaller, we could substitute that into our equation, and it would ultimately lead to a shift in our equilibrium. And so our partial pressures for all of our gases would increase by 3. If we were to factor in our exponents here, so our NO term and our NO2 term are both squared, you can see here. So that would change both of those terms to being 9. Then if we were to combine terms in our numerator, we would have 27 over 9, and that is ultimately equal to Q of the system being 3 times K. If we were to, again, decrease the size of our container volume by 3 times, then Q would be tripled. K for this particular reaction. Okay. And so something I should mention here as well that I don't believe is on that slide is this will only affect things that have different number of moles of gases between our reactants and our products. So you can see in our reactants here, we have 2 moles of our reactant gas, and we would have 3 moles of our product gas total, 2 from our NO and 1 from our oxygen. And so if we have the same number of moles between our reactant side and our product side, then we won't actually see a shift in our equilibrium because essentially those number of moles are the same, and so our partial pressures would not change. Okay. All right, and finally, for our pre-lecture video, we can also talk about the effect of temperature on equilibrium. And so I believe I've said before, but we'll state now officially, any equilibrium constant K is going to be temperature dependent. This ultimately relates back to our ratio between our forward and reverse reactions, which are, of course, ultimately derived from our Arrhenius equation. So if we're thinking about doing a reaction quotient interpretation, though, it's much easier to think of things in terms of enthalpy of a reaction. And so for reactions that are exothermic, we could consider heat to be a product, whereas for any endothermic reaction, we could consider heat to be a reactant. And so if, for example, if we had this reaction here where we have N2O4, it's decomposing into 2NO2. Both of these are gases. And we're told that the heat of enthalpy for this reaction is plus 57.2, that would mean this is an endothermic reaction, meaning we can consider heat to be a reactant there. And so if we were to raise the temperature of this system, if this were in an ampule, then that would be like adding more reactant, and so our equilibrium would shift to the right towards our products, right? If we were to cool the system, however, the opposite, of course, would be true, where if we were to cool the system, the reaction would be like losing some of our reactant, so our equilibrium would shift to the left. Okay. All right. I hope that was informative. If you have any questions, of course, feel free to email or bring them up in class, and we can talk about them. Hope you have a good day, and I will see you in class.